Welcome friends. Today here two figures I am showing. The first figure, when we are observing the lemon is placed in some liquid. In the second photograph, two glasses filled with certain liquids, water and glycerin and some others. So in these all we are putting the lemons. So in which case the lemon is in the bulged shape, magnified shape, not its exactly original shape. It is clear? Here the figure, when we are talking, the lemon and the other cases are not same. Why it is happening? Why it is happening? That we are going to learn today. That's a lesson that is nothing but refraction of light. Today we are going to learn about refraction of light. Is the size depend upon the shape of the glass that we are using? The glass, see, here and here the sizes are different. Here the curved shape, when we are talking about this is the curved shape, here the total one is, whereas here the glass is cylindrical in shape, means. And one more question, that is it depend upon the liquids here present, means the shape, that visibility is occurring due to all these factors, means the curveness of the whatever visible container of the glass, at the same time the liquid present. Even my question is whether it depends upon the shape of the object. So to search, to find the result of all, we will see one by one. So what is the fact that refraction of light is bringing these different shapes, which depends upon the shape of the curved surface of this glass, the present over the liquid, and all. We will find them relations and we will obtain the method and the principle, concept, everything. Here see, bending of pencil from the lower class itself we learned, when we are keeping a pencil inside the liquid jar, so that bends exactly at the liquid surface. So instead of, if you see, we are taking a straight pencil, this is the empty glass, so we are pouring the water and we are putting this dip into that pencil, then there is a bending exactly at the liquid surface. Why it is happening? Again the same thing here we will learn about refraction. So what is refraction means? The refraction here, refraction is the phenomenon of change in the path of light as it travels from one transparent medium to another transparent medium. Means the velocity of what we call this light is changing, the speed is changing from one medium to another medium. Here whenever the change is occurring, then we can notice the bending. So in which direction this light bends? So it can also be defined as the phenomenon of change in speed of light from one transparent medium to another transparent medium, that we already discussed. So here laws of refraction, the incident ray and the normal of the refracting surface at the point of incident and the refracted ray all lie in the same plane. This is one of the important, there are two laws. One is laws of refraction. First law means the incident ray, refracted ray and normal lies in the same plane. What is the second law? This is most important, which we named as Snell's law. The Snell's law says for a given pair of media and for light of a given wavelength, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. For a given pair of media, always these ratios, sine of angle of incidence to the sine of angle of refraction, is always constant. That is known as refractive index. That's what we call refractive index. What is refractive index? Here see, the refractive index of the second medium with respect to the first medium is defined as the ratio of the sine of angle of incidence in the first medium to the sine of the angle of refraction in the second medium. This constant is named as refractive index. This value is always constant. So when we are talking about the refractive index of second medium with respect to the first medium is equal to sin I by sin r. This is the formula. This formula we know, sin I by sin r. And when we are talking about the same speed of light in first medium by speed of light in second medium. Means you can express the refractive index in terms of both sine angles ratio or speeds ratio in the two mediums. Here see, when the light is traveling, it is bending when it is traveling through the glass slab. This straight ray is deviated. So now the speed when we are talking about, if the first medium is vacuum or air, then the refractive index is called absolute refractive index. So for example, if I am talking about what is the refractive index of water, 4 by 3. What is the refractive index of glass? 3 by 2. These are the absolute refractive index. These are absolute refractive index. If c is the speed of light in air and v is the speed of light in the medium, then the absolute refractive index is simply given by this formula: speed of light in air by speed of light in vacuum, c by v. This c by v, the refractive index is simply defined as c by v. Next, we can also have various formulas to know this refractive index in terms of wavelength, real depth, apparent depth, and critical angle. So these one by one we will see, because light here, whenever we are considering it is a wave, the speed of light v is equal to nu lambda. Nu is the frequency, lambda is wavelength. Then the refractive index of second medium with respect to the first medium n2 is n2 by n1. Velocity of first medium by velocity of second medium. So next we are talking about 1 by sin I is a critical angle, real depth by apparent depth, sin I by sin r, lambda 1 by lambda 2. Next, if we are traveling, means instead of second medium to first medium, yeah, first medium to second medium, if you interchange the path of the light, then we will obtain the reciprocal of refractive index of 1 by n12, that is equal to n21. Means n21 reciprocal when the light is reversibility principle of reversibility. If the light travels from second medium to first medium, first medium to second medium, their product is always equal to 1. Their product is what? Always equal to 1. Here see, when we are talking about the refractive index of denser medium with respect to rarer medium is more than 1, and that of rarer medium with respect to denser medium is always less than 1. The second point, if you look at in refraction, the velocity and wavelength of light change. In refraction, the frequency and phase of light do not change. What are changing? Wavelength is changing. Speed is changing. That's why when we are talking about the formula, in this formula, see here we are talking about the refractive index in terms of speed, in terms of wavelength, in terms of speed and in terms of wavelength we are talking about. But we are not talking about in terms of frequency in the expression, because frequency is constant, the phase is constant. So now the denser medium whose refractive index is higher, yes, denser medium is higher than the rarer medium. Now what exactly the rays when we are talking about is sin I, sin r, SAR, then how can we measure? Where is that? See, if the ray is normally incidenting, and when this ray is normally incidenting, the angle of incidence is 0. Where is the angle of incidence? Where is the angle of incidence here? See, this is the normal and this is the incident ray. The angle between incident ray to the normal is known as angle of incidence. This is the refracted ray. This is the normal, of course. The angle between refracted ray to the normal is known as angle of refraction. So angle I is angle of incidence, angle R is angle of refraction. These sin I by sin R here we are talking about. Sin I by sin R is nothing but refractive index of these mediums. Now what happens if a ray is striking normal? Means the angle of incidence in this case is 0. Then angle of refraction is also 0. Why the angle of incidence 0? Why the angle of refraction is 0? Because sin I, when we are talking about here in this formula, sin I is 0. When the ray is striking normal, the angle of incidence is 0, then sin I is 0. So sin I is 0, the refractive index here is 0. When this refractive index is 0, means for that ray there is no difference of medium. The ray cannot change, no deviation. Here see, the deviation is there, d is there, means the refraction can be noticed when the ray of light incident the intermediate mediums, interface of these mediums, then we can observe the bending. If the ray is incidenting in normal, then we cannot observe any bend of the ray, means it travels as such, it is moving inside a same medium, it does not notice the variation of densities. Okay, in this case there is no change in the speed of light, but here one word I use, there is no change in the speed, it is wrong, because here it is not bending. It doesn't mean that the speed here, the velocity of light here, both are same. No, whatever the speed here, the same speed here, whatever the speed of light here, the same speed of light here, but the refractive index here 0 because sin I is 0, because sin I is 0, I value is here, angle of incidence is 0. That is the reason we are not getting any deviated angle here. This is the only fact. That here see, when the ray is traveling, when we are keeping a glass slab in the path, the ray, incident ray it is named, next this is refracted ray, next this is the emergent ray. If this PQRS glass slab is not there, the ray travels straight apart, the ray travels straight apart. So this is the direction of incident ray and this is the emergent ray. The difference between here, this xy, is nothing but lateral shift. So this is the lateral shift. One thing you should observe, the angle of emergence Ex and the angle of incidence, these two, is there any variation of these two? No, these two are equal. So that is the reason there is a shift in the ray. When it is traveling through a glass slab, what is happening? There is a shift, parallel shift in the ray position. So when we are using a glass slab to observe anything, we notice the variation. We notice the variation. When we look at certain refractive index values of the mediums, because refractive index we learnt the refractive index of various mediums. Here if you observe, water has 1.33, as I said earlier, 4/3, crown glass 1.52, rock salt 1.5, means different mediums has the different refractive index. It doesn't mean that no two mediums have the same refractive index. Maybe possible, maybe exist. So those two are simply said to have the same optical density. Here we see what is the meaning of optical density and all. Now see, the medium, when we are talking about the medium and refractive index values, when we are observing the low density, we are taking the top, and high density in the sequence, means rising sequence. If you see vacuum to diamond, the value of refractive index is gradually increasing to reach 2.4. So diamond has the high density, optically high density, so its refractive index naturally must have. Yes. Now sugar solution and all we are having. So now the optically denser medium, here we are talking what is the medium has the density variation. So due to the density variation, it is affecting the speed. Because of the change in speed, we are observing the bending of light. Next thing, if you are talking of optical density and matter density, are two different concepts. What are optical density means? Now we have seen this, just the change in the speed. Okay, whereas matter density means mass per unit volume. So these two are two quite different, though they have the same term density, but these two are not same. Here see, to get clarity here, it is not necessary that an optically denser medium may possess greater mass density than an optically rarer medium. Similarly, here some examples we can quote here. Kerosene and turpentine. Though this kerosene and turpentine optically denser than water, but their mass density is lesser because these oils are float on the surface of water. So optical density is different and mass density are different. Don't confuse by these terms. Optical density is purely decided by the speed of the light traveling, how much fast they are traveling in the given medium. Next, water is 4 by 3 and the glass earlier what I said 3 by 2. So if suppose I am asking about what is the refractive index of water with respect to the glass, then this 4 by 3 by 3 by 2, the ratio gives us the relative refractive index, whereas 4 by 3 is the absolute refractive index of water, 3 by 2 is the absolute refractive index of glass. Next part, when we are going relationship of refractive index to real and apparent depth. Real and apparent depth. If suppose any object is kept here, an object, the ray is traveling like and reaching the eye. So instead of this object O, we observe the object here. This is known as the apparent shift. The apparent shift, the figure when we are discussing about, we will see this figure even see here. If a coin is placed here, when someone is observing, so for him the coin is appears here but not here. This is called apparent shift. If this is the water surface, this is the real depth and this is the apparent depth. So why it is happening so? Again we name it the phenomena refraction of light. So earlier I have shown the formula, the refractive index is equal to real depth by apparent depth. From where we are getting? Here we are getting real depth by apparent depth. So real depth by apparent depth, how we are getting this? This formula is, the derivation part is very simple. If you see OPN is a triangle, right triangle, and IPN is another right triangle. There are two right triangles. So OPN when we are having, and I here one more NPI. So for both having the 90 degrees. This is the angle of incidence. This is the angle of refraction when we are talking about. Then alternate interior angles RR, and here I are corresponding angles, corresponding angles between these two. When these corresponding angles and alternate interior angles we are having, the definition N is equal to sin I by sin R. So from this triangle, bigger triangle, sin I by sin R, when we are talking about PN by IP, and sin R, the what we have this bigger and smaller triangles, the ratios corresponding. See, this is the R, so this is the ratio. So sin R here, see, sin R is equal to PN by OP, and sin I is equal to what we are having, opposite side by hypotenuse, PN by IP. The ratio gives OP by IP. OP, what is OP? OP is this distance, IP is this distance. For smaller angles, sin I is approximately equal to I, sin R is approximately equal to R. At the same time, this is very small, this OP can be taken as ON, OR can be, sorry, IP can be taken as IN. So when we replace, this gives the real depth by apparent depth, this formula. So real depth by apparent depth is nothing but refractive index. When we draw the graph, so real depth to apparent depth, what kind of the graph we are getting? We are getting a linear graph, that straight line passing through origin O. It means here refractive index, the slope gives us what? The slope of the graph always gives us refractive index. Now the real depth and apparent depth are in direct proportionality. They are always direct proportional to each other, and the constant of proportionality is nothing but here refractive index. So we get a linear graph. You can do this experiment if you interested. We can have the experiment to know Next, the phenomena named total internal reflection. What is total internal reflection? If you see, this is a denser medium and this is the rarer medium. If the source is in the denser medium, the source means emits light, the light travels from denser to rarer. What is happening? It moves away from the normal because of the change in the speed of light, at the same time refractive index, so the deviation will be more. Similarly, when we are going and taking the different incident rays, if the angle of incidence gradually increases certain angle here, see, it is just grazing along the interface, and more than that angle the ray is further deviate, means it re-enter into the same medium. Such phenomena means re-entering of incident ray into the same medium is called TIR, total internal reflection. Means the total internal reflection, what is the condition? The angle here, see, the angle of incidence must be critical angle. This angle is called critical angle, equivalent to critical angle or more than the critical angle. Okay, this is the boundary condition. More than that, it re-enters, and the source always here in the denser medium. These are the two conditions. So various phenomena based on the natural phenomena, that is nothing but mirrors. One of the natural phenomena that is happening, mirrors. See, in the hot sunny days we can have such images. There's such a pond is there and it is producing the image of that whatever the bush or shrub or something tree. So in fact there is no water here nearby. This is happening due to the total internal reflection. Looming is the phenomena happens the same based on the total internal reflection in the quadrant regions. So the object seems to be somewhat raised high to the horizon. So this what we, and the most important is optical fibers. Nowadays we are using this total internal reflection based working optical fibers. This based on optical fibers. These optical fibers are used in communication system, the fast networking. You have the broadband to the home, DTH or something words you are using. So all these are based on the optical fibers. Okay. Next, totally internally reflecting prisms. These are used in the binoculars. Next phenomena, atmospheric refraction. This atmospheric refraction, what is happening? Advanced sunrise and delayed sunset. This is the what you call the horizon, and suppose the sun is here, actual position of the sun, the rays coming from here, it has to go straight, but they are deviating towards, because when we are talking about the various layers of the atmosphere, the various layers of the atmosphere having the various densities, due to the optical density variation, the ray travels from rare to denser, so denser to rarer, whatever this we discuss refraction phenomena. Because based on the refractive index, the bending taking place and goes on and reaching here. For a person who is standing here, he will see that position of the sun is here. So this before actual sunrise, because origins below the sun is here situated, but he can able to see because of the refraction, is named as atmospheric refraction. Atmospheric refraction is causing delay in sunset and advanced sunrise. Each takes place 2 minutes before the actual sunrise. We can see the sun. Similarly, after sunset, the actual sunset happens. Even then, we can observe the sun 2 minutes. So total this sunrise time 2 minutes extra we are getting, and sunset delay that 2 minutes we are getting, total 4 minutes in the duration of the sunlight. That's what we are getting, the day length. Next, twinkling of stars is the another one. Is it is also happening, the refraction of light. The various atmospheric layers, the densities see here, changing atmospheric layer densities, greater air density at the here, also the greater air density or low air density. The same thing here also, the star, the rays when they are coming, they have to travel, undergo various dense layers. So due to this, the apparent position of the star is not, instead of this, it is seems to be changed. So this red marked one, it is changed and it appears like here instead of here. So this makes twinkling, because this atmospheric density, the layers of the atmosphere is also not steadily or constant or not stationary. They fluctuate. Due to the fluctuation, there is a continuous flickering in the ray path of light. So this makes us the twinkling effect. This makes us the twinkling effect. Now refraction by spherical lenses we will see in the second video. In the next video we will see this.